Hello everyone, welcome to lecture number 41 of this NPTEL course on Riemannian geometry. So let me remind you of what we did in the previous lecture. So we defined this function d of p comma q for any 2 points pq in M. So this was simply the infimum of the lengths of sigma over all possible sigmas joining p and q, all possible admissible paths sigma joining p and q. Then we saw that d actually defines a metric or a distance function on M. So because we already have this notion of Riemannian metric, maybe using the word metric might sometimes be confusing, so I will keep calling it the distance function. And in fact we saw that the topology on M with this distance function, so of course the topology on this pair is basically induced by these balls, metric balls, which form a basis for this topology. It turns out that this metric space topology actually coincides with the existing topology on M as a smooth manifold, right. So M already has a topology since it is a smooth manifold. This new topology using the distance function actually coincides with the topology that is already there on M, okay. Alright, so today I would like to explore this notion of completeness for this metric space. So I want to talk about what is called as geodesic completeness. Okay. Right, so here is a definition, or let me first remind you of what metric completeness is. So recall this M comma D is called complete if for all Cauchy sequences. So if all Cauchy sequences are convergent. Okay, that is if Qk is a sequence such that for all epsilon there exists a capital N such that the distance between Qj and Qk is less than epsilon for all Jk bigger than N, then Qk converges to some Q in M, okay. So this is the notion of metric completeness, right. So here is the definition of geodesic completeness. So we say that a Riemannian manifold M comma G is geodesically complete if for all points on the manifold the domain of the exponential map is the entire tangent space, okay. Or equivalently all geodesics last for all time, right, because all geodesics are of the form exponential p of Tv for some p and some v, then the fact that the domain of the exponential map is the entire tangent space is equivalent to saying that all these geodesics last for all time, okay. Or equivalently in our in a notation that we introduced a bit earlier, if you look at the maximal time of existence for a geodesic whose initial velocity vector is given by p, then this is all of R, okay. Right, so just to give you a sort of quick example, all the nice Riemannian manifolds that we have looked at, so for instance all the model spaces these are geodesically complete. So in fact for the case of the sphere we wrote down exactly all possible geodesics and we saw that they lasted for all time, right. So essentially you just go around the great circle ad infinitum, right. On the other hand, if you take let us say the unit disk inside R2 with not the Poincare disk metric, which is geodesically complete because that is isometric to the hyperbolic space. No, but you take the restriction of the usual Euclidean metric, then this is not geodesically complete. We have already seen this because let me draw a picture. So this is the unit disk at the origin. Suppose you have a point P here, if you take a tangent vector in this direction, soon enough you will basically hit the boundary of the disk and you cannot continue, right. So these are this is clearly not geodesically complete. So now we have two notions of completeness, one as a metric space, one as a Riemannian manifold. Natural question is, do these coincide, and happily for us they do, and that is the content of the next theorem, one of the sort of most important theorems in classical Riemannian geometry called the Hopf-Rinow theorem. Okay. So this says the following are equivalent. I am going to write down 4 conditions, it turns out all 4 are equivalent. So the first is that MD is complete as a metric space. Second, Mg is complete as a Riemannian manifold, so it is geodesically complete. The third point is that there exists some point P such that the domain of the exponential map is the whole tangent space. So remember, completeness, geodesic completeness demands that this holds for all P, but it turns out as we shall see that this is equivalent to just testing for a single point. So for a single point, if the domain of the exponential map is the entire tangent space, then Mg is geodesically complete. And fourth, M satisfies the so called Bolzano-Weierstrass property, okay, which says that every closed and bounded set is compact. So of course this is not true in general metric spaces. On the other hand, in R, this is, if you remember from your analysis course, this is a very convenient criteria for checking compactness for subsets of the Euclidean space. All you need to do is to check that they are closed and bounded. But it turns out that the same thing is also true for geodesically complete Riemannian manifolds. Moreover, and this is sort of the key part, moreover all of these, I mean these are equivalent, so each one imply the fifth property, that is for all PQ in M there exists a unit speed minimal geodesic. I mean, of course unit speed is not important. If you have some minimal geodesic, you can just reparameterize to have unit speed. Okay. All right. So in the next, I mean in this and the next lecture I am going to prove this theorem. So it all relies on a key condition, on a key statement, which is sort of a version of 5 but for a single point P. Okay. So consider the following statement, which I am going to label by star or label by sort of hashtag. So this statement is the following. So let P be in M such that the third property holds, that the exponential map at P is the domain of the exponential map is all of TPM. Then for all other points Q in M, there exists a minimal geodesic connecting from P to Q. Okay, so suppose you know that the exponential map, the domain of the exponential map at a single P is all of TPM. Then for any other points Q, you can join them, you can connect them to P by a minimal geodesic. Okay. So this is sort of a, I mean, as I said, this is a version of phi, but for where you now fix this point P, okay, and only allow Q to vary. So it will turn out that this hashtag is really the heart of the matter. That is the hardest part of the proof. So the proof follows a slightly sort of complicated flow. So let me denote the flow of the proof. Okay. So I am going to first show that 1 implies 2, and then that trivially implies 3. I am then going to show that that 3 so 3 implies 4 using star. Okay. So if condition 3 holds, then I am going to show that star holds. So in the intermediate step, I am going to have that star is implied by so in the intermediate step I am going to show that star is true. The statement star is true, and then using the statement star and 3 once again I am going to show the Bolzano-Weierstrass property, and then this is going to imply 1. Okay. And then finally apply star to all points P. So this will imply that 2 geodesic completeness implies property number 5, and so then I'll be done. Okay. So as I was saying, this is really the hard part. I'll prove this next time. I'll prove the rest of Hopf-Rinow modulo, sorry, this is not star, this I am calling it hashtag, right. Okay. So modulo this statement hashtag, I will complete the proof of Hopf-Rinow, and then in the next lecture I will prove this statement hashtag, right. Okay. So let's go to the proof of Hopf-Rinow. So let's first prove 1 implies 2. Okay. So suppose MD is complete, but suppose the Riemannian manifold is not complete. Okay. So then there exists a point P and a tangent vector at that point such that the corresponding maximal interval for existence of the geodesic is not all of R. And without loss of generality, I can always normalize my V to be 1, right. So then there are 2 possibilities, so 2 cases. So case A is that so case 1 is that if you take the supremum of this set IV, then that is less than infinity, right. Or the second case that the infimum is not minus infinity, right, or of course both can happen. So let us first analyze case 1, the second case is similar. So suppose we are in case 1. Okay. So then the situation is the following. So you have your P here, you have your gamma that ceases to exist beyond a certain point. So P, I mean without loss of generality I can assume that 0 belongs to the interval by just translation. So I am assuming that P is gamma of 0. So now I do the following. So suppose right, so let Tk be equal to B minus 1 by k. So remember B is the supremum of IV, so that is the sort of maximal time of existence of the geodesic, and let Qk be equal to gamma of Tk. Okay. So these are these sort of points that are leading up to the maximal existence of your geodesic, and recall that gamma of T is simply exponential of Tv. Okay. Right. So now if let us say if Tj is less than Tk, I want to claim that these Qk's actually form a Cauchy sequence. Okay. So why is that? Let us estimate the distance between Qj and Qk. Well, that is obviously going to be less than the length of the part of gamma between Tj and Tk, but gamma is unit speed, so this is obviously sort of Tk minus Tj. Okay. So in general the distance between Qj and Qk is less than the absolute value Tj minus Tk, but what is that? That is precisely just 1 by j minus 1 by k. Okay. So clearly this can be made smaller than epsilon if jk are bigger than some n. Okay, for some n. Okay, you can for instance choose any n which is bigger than 2 by epsilon or something. Okay, so this implies that Qj is a Cauchy sequence. So by metric completeness there exists a Q which is the limit of these Qj's or Qk's, right. Okay, so now let me draw a little, so all of these converge to some point Q here. Let me just draw a geodesic ball around Q. Okay. So let UP epsilon be a geodesic ball around Q of radius epsilon. Actually more than, sorry, let me rephrase that. So let U be a neighborhood of Q. I do not actually need it to be a geodesic ball, such that for all points x in U and for all tangent vectors W with norm of W less than 1, the corresponding geodesic exists at least for time interval epsilon. Okay. Okay, so then by uniqueness, suppose we take wk to be the velocity vector at qk and k large enough such that qk belongs to this neighborhood u, right, because qk is converged to q, obviously for some large k, qk is going to be contained in u. Then by the uniqueness of geodesics, if you take the corresponding geodesic gamma w, so the picture is the following. You have this velocity vector. Now with this velocity vector wk, the geodesic is unique, right, by our basic uniqueness existence and uniqueness theorem. So that means that this geodesic gamma w must coincide with the geodesic that you already have, at least in a neighborhood of that point. Okay, so formally if you write it down, you know that this is equal to gamma of tk plus s for all s in the interval minus epsilon to epsilon, right. But now just consider sigma, which is given by gamma of t all the way up to b, and it is given by gamma w of t minus b, sorry, t minus tk for tk between for t between tk and tk plus epsilon, okay, where we choose tk for k large enough such that tk plus epsilon is strictly bigger than b. So the idea is the following, that you already I mean in this pink neighborhood you have a geodesic with this initial velocity vector, but which lasts for at least a time epsilon. Now if you choose qk close enough to q, then if you have this new geodesic that lasts for a time at least epsilon, then that epsilon time will take you beyond the point beyond the time t equals b, right. So that would basically give you an extension of your geodesic, contradicting the fact that b was the maximal time, okay. So then clearly sigma is a geodesic. Why? Because wherever these two times intersect we have this, right. So sigma is a well defined smooth geodesic, but sigma sort of exists on the time interval 0 to tk plus epsilon, which contains the closed interval 0 to b, okay, strictly contains the closed interval 0 to b. So this gives an extension of gamma, so this contradicts the maximality of b, okay. Alright, so this shows that 1 implies 2, metric completeness implies geodesic completeness. Now obviously 2 implies 3 by definition, because 2 says that for all p the domain of the exponential map is the entire tangent space, whereas 3 says that there exists some p for which this holds, so obviously 2 will imply 3. Okay, so now I want to show that 3 implies 4 assuming star, okay. So as I said, sorry, assuming hashtag. and as I said I will prove hashtag next time in the next lecture. So I have to prove the Bolzano-Weierstrass property. So let S be closed and bounded. So let R be the supremum of the distance from x to p, where x is in S. Okay. Then because S is bounded, R is a finite number, right. So here of course P is such that the exponential map at P is the entire tangent space, right. So I am assuming that such a P exists because I am assuming that 3 holds. Okay, so let K be the closure of the image, sorry, be the image of the closure of this ball in the tangent space under the exponential map. Okay, this is well defined, or this is actually defined because EP is equal to this, right. So the exponential map is defined on that ball in the tangent space. Also by the Bolzano-Weierstrass property, so TPM is basically just Rn with the metric GP, right. Then of course by choosing a basis for the tangent space, you can say that that TPM is in fact isometric to Rn with the usual metric by just choosing a basis, an orthonormal basis for TPM. But then one can use the Bolzano-Weierstrass property of Rn implies that K is compact, okay, and because also the exponential map is continuous. So the Bolzano-Weierstrass property implies that this closure of this ball is compact, and then because the exponential map is continuous, the image under the exponential map will also be compact, okay. Now my claim is that S is in fact contained inside this set. So claim is that S is actually contained inside K. If I show this, then I am done, because then S will be a closed subset of a compact set, so it has to be compact, okay. So why is this true? So let Q be any point in S, then by hashtag there exists a minimal geodesic gamma from 0 to L, let us say, such that gamma of 0 is P and gamma of L is Q. Okay, one can in fact write gamma of t as the exponential of TV, where V is some unit vector. So I am reparameterizing so that gamma is unit speed and L is simply the distance from P to Q. So then clearly L is less than equal to R, right, because R is the supremum over the distance from P to X for any point X in S. So clearly L is less than equal to R, which means that if you take the point LV in the tangent space, the norm of this is also going to be less than equal to R, because V is chosen to be a unit vector, or in other words LV is contained in the closure of this ball in the tangent space. But then Q, which is simply the exponential of LV, is then contained inside gamma. So Q was arbitrary, so this implies that S is a subset of K, and then as I said we are done. Okay. So finally, let me explain that that 4 implies 1. This is true for all metric spaces. So actually maybe let me just leave this as an exercise. This is just a exercise in point set topology, right. So given the Bolzano-Weierstrass property, suppose you are given a Cauchy sequence, then by the triangle inequality any Cauchy sequence is a bounded sequence. So by the Bolzano-Weierstrass property, its closure is going to be compact, which means that that there is going to be a subsequence that is convergent, but if a subsequence of a Cauchy sequence is converging to something, the entire sequence must converge to that, right. So that is essentially the proof of 4 implies 1. It is just a exercise in point set topology. So let me end the lecture with the following remark. We can actually right, so we can actually prove directly that if you have the property 2 and the property 5, so the fact that you are working on a geodesically complete manifold, and let us say you also know that given any 2 points you have a minimal geodesic between them, then this actually implies metric completeness. So the proof of this uses a trick that is used often in Riemannian geometry. So I thought I will also prove this implication for you directly. Of course this follows from our sequence of implications earlier, but I thought that because this, as I said, this uses a trick that shows up a lot of times, I will give you the direct proof. So let us fix a point P in M, and suppose Qk is a Cauchy sequence. Okay. So actually sorry, I should have said that in fact the property 3 and hashtag directly prove property 1. Okay. Right. So fix P such that the exponential map is defined everywhere. Okay, and let Qk be a Cauchy sequence. So then by hashtag for all k there exists unit vectors such that Qk is given by the exponential of Lk times Vk, where Lk is precisely the distance from P to Qk. So in other words, I am saying that if you look at the geodesic gamma k given by the exponential of T times Vk, this is the minimal geodesic from P to Qk. Okay, where T is between 0 and Lk. So by hashtag such a minimal geodesic exists. Alright, now because Qk is Cauchy, it is bounded, which means that the sequence Lk is bounded. Okay. So after passing to a subsequence, which I will continue to denote by Lk for ease of notation, these Lk's converge to some L infinity. Similarly, all the Vk's have norm 1. So again the unit sphere is is compact. So, by the Bolzano-Weierstrass property, after passing to a subsequence, so the Bolzano-Weierstrass property in Rn, okay, I am not using the Bolzano-Weierstrass property on M, just by the Bolzano-Weierstrass property in Rn, again up to passing to a subsequence, Vk is converged to some unit vector V infinity. Okay. Okay, now consider the following. So, let gamma infinity of t be simply the exponential t v infinity, and let q infinity be equal to the image at L infinity. Okay. Then clearly q infinity is going to be the limit of all these qk's, right, because each of these qk's is basically the exponential of Lk Vk, and Lk is converged to L infinity, Vk is converged to V infinity, Exp is obviously a continuous map, right. So, so we started with the Cauchy sequence Qk, and now we have constructed a limit. So, every Cauchy sequence is a limit. This implies that MD is complete. Okay, so this completes the proof, direct proof from 2 and hashtag to 1. Okay. All right. So this completes the proof of Hopf-Rinow modulo proving hashtag. So, in the next lecture I will prove the statement hashtag. Okay. All right. So, that is it for now. Thank you for your attention, and I will see you next time around.